Solving the Kepler problem using only Newton's laws, high school level math, and an intuitive approach to the concept of limits. Video 2, Proving Kepler's second law. Planets sweep out equal areas in equal times. We can state the law in terms of symbolic algebra as A is proportional to T. Or A equals K times T, where K is a constant for a particular orbit. Remember K for Kepler, or K for Kepler's second law. Now Kepler realized that a planet's speed is slower when r is greater. Thus, the planet travels farther on the left side of this diagram than on the right, but the area swept out is the same. The most general way of expressing this law is to state it as follows using the delta symbol. Any change in area divided by the corresponding change in time equals k, our constant. And if we want to think microscopically, we would say that dA over dt equals k, or dA equals k times dt. Let's begin our effort to prove the second law of Kepler by exploring Newton's second law of motion a bit. Galileo showed that acceleration is just change in velocity divided by the time lapse, as long as the force is constant. So we can rewrite Newton's second law as force equals mass times a change in velocity divided by a change in time. Now if we multiply both sides by delta t, we get this equation, and we can see that the two delta t's on the right will cancel out, and we will be left with force times delta t equals mass times delta v. In physics, force times delta t is sometimes such a useful concept that it has acquired a special name, impulse, which we designate with a capital I. The concept of an impulse is particularly useful when a force is applied for only a very brief period of time, such as vividly illustrated in this photograph. For the definition of impulse that we are using to be true, the force must be constant. We will be applying the concept to the force of gravity for brief moments, when the distance of the planet from the sun is effectively unchanging, so that we can treat the gravitational force as a constant for that brief moment. Just so you know where we are going with this, we will soon conduct a thought experiment in which we turn gravity on and off for very brief instants. So now we write that I equals mass times a change in velocity. It will be convenient to consider an impulse divided by the mass of the planet, and we can call that the specific impulse, or the impulse per unit mass. So now we have a very simple equation. The specific impulse caused by turning gravity on for a brief instant equals the change in the planet's velocity. Now let's relate all of this to gravity. We can rewrite this equation, I equals the force of gravity times delta t, as follows, using Newton's universal law of gravitation. Now let's divide both sides by m to get the specific impulse. The quantity g times big M, the mass of the Sun, divided by r squared, is known as the gravitational field, which we designate with a cursive F and a G subscript. We can remember it simply as the gravitational force divided by little m. So the specific impulse equals the gravitational field times delta t, which in turn equals delta v. From now on, we will be dealing only with specific impulses, which I will sometimes refer to simply as impulses for short. So here's our setup. We have a planet at position A at noon on a particular day, and gravity is turned off. Now let's give the planet an initial velocity. Going forward, all velocity vectors indicating direction of the planet's motion will be blue. Delta velocity vectors, or delta v vectors, caused by the force of gravity, will be red. Displacement vectors denoting the change in a planet's position will be orange. An underscored v refers to the actual vector having both magnitude and direction. A v that is not underscored refers only to the absolute value, or magnitude of the vector. Note that although we distinguish between velocity vectors and delta velocity vectors, they both belong to the same general class of velocity vectors, and therefore they can be added together. In contrast, it would not make any physical sense to add a velocity vector to a displacement vector. Now, I have chosen to scale velocity vectors so that their magnitude also indicates the distance traveled in 1 hour. So, if we look at the situation at 1 p.m., we can replace the blue vector here with the displacement vector here showing the change in the planet's position over the previous hour. Now, by Newton's law of inertia, the planet's velocity has not changed, so we can add in the same velocity vector as before, but we associate it with the planet at position B. I just want to stress once again that the length of the displacement vector is simply v times delta t, where delta t equals 1 hour in this case. Now we turn on gravity so that the planet experiences a gravitational field for a brief moment. In accordance with the informal convention that we have established, we indicate that brief moment as dt. Therefore, the gravitational field times dt equals the specific impulse, which in turn produces a change in the velocity of the planet, a delta v. This was exactly Newton's line of reasoning. As he put it, let it be attracted towards the center S by one impulse or impression of force. Now we turn gravity off and we freeze time. We have two velocity vectors and we can add them. We add two vectors by positioning the tail of one vector at the head of the other. In this case, we position the tail of the red vector at the head of the blue vector. And we construct the resultant by drawing a new third velocity vector from the tail of the original blue vector to the head of the red one. After 1 hour, the planet arrives at point C prime. I call it C' because the planet would have arrived at point C, shown here, if gravity had not been turned on. Now let's go back in time to noon. We are going to construct 3 triangles and show that their areas are all equal. We begin as before, but we don't turn gravity on at 1 p.m. The planet continues on a straight path due to the law of inertia. At 2 p.m., the planet arrives at point C. We now construct triangles X and Y as shown. We consider the purple line segment from S to B as the base of both triangles. Next, we construct the altitudes of X and Y as shown. Let's consider now the 2 red triangles shown here. Let's zoom in so we can see better. Each triangle has a side consisting of one of the 2 displacement vectors. In accordance with the setup of this thought experiment, these 2 displacement vectors are equal in length. Both triangles contain a right angle consistent with the construction of the altitudes of X and Y. The angles indicated here in pink are equal because they are opposite angles of intersecting lines. The 2 red triangles are congruent in accordance with the 2 angles and 1 side rule. Therefore, the dotted blue lines, representing the altitudes of X and Y, are equal. So the areas of X and Y must be equal because they share the same base and their altitudes are equal. Now we go back to 1 p.m. and turn gravity on for a brief instant as we did earlier. We add the blue and red vectors as before and let 1 hour elapse. The planet is now at point C'. And we construct the 2 triangles shown here. One of them is Y from before. And we label the new triangle Z. We draw their altitudes. And we note the following. When we move the tail of the red vector from point B to point C in order to add it to the blue vector as shown here, the 2 images of the red vector are parallel in keeping with the rules of vector addition. Therefore, a line segment connecting C and C' is parallel to the base of both triangles, represented by the purple line segment, and it follows that the 2 altitudes are equal. We have proven that the areas of Y and Z must be equal, once again because they share the same base and have equal altitudes. So the areas of X and Z must be equal because they are both equal to the area of Y. We have just shown that in this thought experiment, the planet has swept out equal areas from noon to 1 p.m. and from 1 p.m. to 2 p.m. If we continued this thought experiment for additional 1-hour intervals, the same logic would always lead us to conclude that the planet always sweeps out the same amount of area in equal time intervals. This is exactly the logic used by Newton as this drawing of his illustrates. Eventually, we would complete some sort of circuit around the sun, but we would not necessarily wind up exactly where we started. However, if the initial conditions were just right, the planet would return to its original position, having followed an orbital path consisting of some irregular polygon. Now, Newton imagines the next obvious step. He reduces the interval between gravitational impulses from delta t to dt, a length of time so close to zero that the result approximates a gravitational field that never turns off. We can imagine that as dt approaches zero, the triangles we would need to draw in our analysis would become thinner and thinner wedges, so that the orbital path would approach a smooth curve.
Note that we are still talking about the areas of triangles, and as these areas get smaller and smaller, we talk about them in terms of dA sub t. Whereas what we are really interested in is the area of a sector of an ellipse, dA sub s. But by now we have developed our intuition regarding the concept of limits enough to feel comfortable taking dA sub s as effectively equivalent to dA sub t, even though it doesn't quite meet the strict definition for the area of the sector according to the theory of limits. Let me remind you why. I'm just showing here two of the triangles that we can imagine we have constructed in our thought experiment. The divisions are not marked off based on equal angles, but rather on equal times. The central angles might vary quite a bit. Now, the definition of area, you recall, of a sector of a closed curve is based on an infinite number of triangles with equal central angles. And although it is true that in accordance with our methodology, A1 equals A2, there are obviously areas in both sectors that are not included in the triangles, and the unincluded area on the right is clearly larger than the unincluded area on the left. However, this discrepancy becomes mitigated as we create more triangles by shrinking delta t. We can see that the amount of area newly included by constructing the two new triangles on the right is greater than the new area included on the left, not only in absolute terms but also in relative terms. Consider that the relative increase in area included, and therefore the relative decrease in error, can be measured in the following way. The new radius, OB, on the right can be divided into two segments, ON and NB. Similarly, the other new radius, OA, on the left can be divided into two segments, OM and MA. The relative increase in included area on the right is proportional to the ratio of NB to ON, which is clearly greater than the ratio of MA to OM. So, wherever the error is greater due to a larger central angle is also where the error gets reduced at the greatest rate as new divisions are made. We have shown that dA sub t to dt is a constant, and that to an acceptable level of certainty, dA sub s divided by dt is also equal to k, and we claim therefore that we have proven Kepler's second law.
You are now ready to proceed to video 3, proving Kepler's first law, his law of ellipses.